Hi guys, in this video we're going to be going through integration using partial fractions. So the reason why we need this skill is because it's going to help us to integrate things like this. So if we were differentiating this, right, so the opposite of integration, if we were differentiating this expression or this function, we could call it, we would just use the quotient rule. We would let the numerator equal u, we'd let the denominator equal v, and we'd go ahead and differentiate. So when we integrate, it's actually a little bit more difficult than that. We have to use something called partial fractions. So the first thing that we're going to do for this question is we're going to express this as two separate fractions. So in this situation, our denominator, so if we look at the denominator of the original expression, we've got two linear factors here. So if we had a quadratic factor or something a little bit more complicated, then we've got to use a different approach when we're splitting this fraction up into separate fractions. So for example, this is a bit of a guide here. So notice you can see that if we've got two linear factors, then we're just going to have a and b on the numerators. If we've got a linear factor, so this second example, if we've got a linear factor combined with a repeated linear factor, then we've got this set up here where we've got a, b, and c, but we've got x plus 1, x minus 2, and then we've got x minus 2 squared on the end. For the third function or expression, we've got a linear factor combined with an irreducible quadratic factor. So that obviously just means that we can't factorize that into something simple, it's irreducible. So in this case, we just have an a on top of x plus 1, but then we've got bx plus c on the numerator of the second fraction. So the reason for that is because this has to be one order below what this was. So this was a irreducible quadratic factor, so therefore the term on the top here has to be linear. Hence bx plus c, which is kind of similar to mx plus c. Then we've got the fourth example here where we're going to have to do long division. I'm not going to cover that in this video, but I will cover that in another video. Okay, so we've done the first part, we've split this fraction up into two separate fractions. Now we just need to find a and b. So in order to find a and b, what we need to do, we need to cross multiply, and then the denominators are going to be matching, so the denominators can cancel. Then we're just going to have the two numerators equal to each other. So at this point, now what we can do is we can just equate the numerators. Now what we're going to do is we need to find a and b, and the way that we're going to do that, so to find out b, we're going to substitute x equals -3 into this equation. The reason why we've chosen -3 is because if I substitute -3 in for x here, then that entire term is going to become 0. So it's going to help us to find b, and then it makes sense that for the next part, we're going to substitute 1, because then this second term is going to cancel, and hence that's going to help us to find a. So we've found out that b is equal to 1. Now we're going to do the same thing to find out a. Okay, so we found out a, we found out b. Now we just go ahead and we put those back into our expression, and then this can now be integrated quite simply. Okay, so notice if we're looking at this example now, the question is exactly the same as before, but we've just got an integral symbol next to it. So we've been asked to integrate this function. So when we're integrating this, if we just look at this step here, now that we've got two separate fractions, we can apply integration to both of those separately, and we're going to end up with 2 ln x minus 1 plus ln of x plus 3. Using log laws, we can go and simplify this a little bit further to get this. So next example, we've now got a repeated linear factor on the denominator. So when I split this up into partial fractions, it's going to look like this here. Then we do some cross multiplying exactly like we did before. So we're at this point here. I'm not going to go and write the denominator because I think that's a little bit of a waste of time. So we're just going to equate the numerators like we already have. Now what we need to be thinking about, we need to be thinking about like what values we should be subbing in for x that are going to help us to solve for a, b, and c. So I've noted that if I substitute 1 into this equation, then this part here is going to cancel. And also this part here is going to cancel. So that's going to help us to find out c. So we've worked out that c is equal to 6. Now we're just going to do the same thing. So we've got a equals 2. Now we're going to go and substitute 0. So now that we're at this step, we can go and substitute a and c into this equation, which will help us to solve for b. Okay, so we now know that we've got b is equal to -2, we've got a is equal to +2, c is equal to +6, and then now we can go and just substitute all of those into our equation, which we've done in the box in blue here. What we could also then go on to do is we could just go on to integrate this, which I've gone ahead and done. So if you wanted to, you could go ahead and look at how I've integrated and follow those steps. Now we're going to do another example, but since we've already done 2 pretty clear examples, I'm just going to talk through this example. So essentially we've got this here. Notice that we've got an irreducible quadratic factor on the denominator. So what that therefore means is that if we go back to our rules for partial fractions, so using our rules for partial fractions, we're going to have to use this rule here. So that explains why I've got this here. Then we do the same sort of process. So you'll notice there's a bit of a pattern with all of these questions. Now I'm just going to simply cross multiply, and then I'm going to equate the numerators. Then I'm going to have to carefully think about what values to substitute. I've chosen to substitute 2 here because this was x minus 2, so that's going to help me to find a. Okay, so we've got our function here. So the first thing that we're going to do is we're going to expand all of this out, and then we're going to collect like terms. At this step, what we're going to do is we're going to group like terms. So we're going to move all of the x squared terms next to each other. We're going to move all of the x terms next to each other. And then we're going to just leave all of the constants with each other. So at this point, now what I'm going to do on the right-hand side is I'm going to factorize x squared out of the first 2 terms. So we're going to have a plus b and then x squared. Then I'm going to do the same thing for all of the x terms. So that would give us, we'd have a minus 2b plus c x. And then we'd just have, I'm just going to write this as a minus 2c. So notice that if we think about looking at the left-hand side, this is going to be a 1 here technically in front of the x squared term. So notice that if we've got a 1 in front of the x squared term, but it's equal to this side here, we can go and equate coefficients. So what I could go and write is I could go and write that 1 is going to be equal to a plus b. In the same way, I could write that 6, so the next term, we're looking here, I could go and write that 6 is going to be equal to a minus 2b plus c. And then I could also go and write that 5, the constant, is going to be equal to a minus 2c. So that process is called equating coefficients. So from this point to solve b and c, we're just going to rearrange the equations. We're going to substitute a equals 3 into them, which is what we worked out before. We worked out that a was equal to 3. So we go ahead, we do some algebra to find c and to find b, then we just put them back into our original equation. So just another example here really quickly. So we've got a question, we've got an irreducible quadratic factor, and we've been asked to find the antiderivative, which is the integral, by expressing in partial fractions first. So first step, as usual, we separate the fraction into partial fractions, we cross multiply and then exclude the denominators. We then think carefully about what values we're going to have to sub into this equation. So then once we've found A, B, and C, we can resolve this into partial fractions. Then all I've done here is I've just separated the second fraction into two so that I can integrate. Now, a bit of a tricky process to integrate here, and not necessarily the purpose of this video, but to go and actually integrate the second term, we would have to use integration by recognition, which is from 12 Methods Unit 3. And then we'd also have to use integration involving inverse trig functions to integrate the third fraction here. And if you're in my class, that's from lesson 3. If you're not in my class and you have access to Cambridge, then you would go to exercise 11C and you can learn a little bit more about integrating involving inverse trig functions. That's it for this video, guys. Thanks for watching.